In this video, we're continuing with the dice simulator. The random numbers are more or less sorted. Now to the LEDs. Last time I suggested you read up on bit set and shift left and try writing your own LED display code. Hope that was a fun challenge. Here's the kind of thing I had in mind. This expects R1 to contain the dice value between 0 and 5. We always start with one LED on, since you can't have rolled less than a 1. Subtracting 1 will only set the carry when the previous value was 0. So if we started with 0, just the first LED will be on. Each time through the loop, we shift the LED's left 1 position and turn on the rightmost one. By the time the loop is finished, the right number of LEDs are lit. That wasn't too bad, was it? You might find it worthwhile to see it working in extreme slow motion by single-stepping through the code. I'll walk you through a debugging session in another video, but try it for yourself with this code. Start by loading R1 with a value between 0 and 5. Then start single-stepping at slot 40. Then you can repeatedly type either S or SS to go step by step. The only difference is that SS shows all the registers. Okay, I think we're done with the live experiments. Let's write the code properly in a text editor on the PC. A lot of programmers don't like writing comments. I've often heard things like, "I'll get it working first, then I'll do the comments." Makes me think they're not too sure what they're doing. Anyhow, I start with comments. They're my instructions to me for what I need to do. The nice thing is they're still there when the code's written, which helps anybody trying to understand it later on. Bear in mind that code is for humans. The computer just wants the bit patterns. Okay, which task should we start with? You might think initialization is a natural thing to start with, but no. What needs to be initialized depends on the details of all the other tasks. So it's pretty much the last thing you write. Let's go with the random number part. Here it is. The first thing you might notice is that I haven't written in slot numbers. Some lines have a label at the start, and jumps have the appropriate label as their target. This makes the code much easier to follow than using slot numbers. ArdEx doesn't understand these labels, but I've written an assembler which runs on the PC and works out the slot numbers for you. The other thing that's new is the call and ret instructions. They're special jump instructions. Call works just like jump, except it also keeps the next instruction's address on a stack. Ret is short for return. It also does a jump, but you don't tell it where. It takes the most recently saved value from the stack and jumps there. In human terms, it's like you're reading a book and reach a word you don't understand. You jot down the page number you were on, look up the word in the dictionary, and then return to the right page in the book. And if there's a word in the dictionary definition you don't understand, you can do another lookup while you still haven't finished the first one. Because each return address is placed on a stack, you can unwind everything cleanly. A stack is often known as a LIFO, last in, first out. This business of a call within a call is known as nesting. On most computers, the stack is in main memory. As you know, ArdEx is tight on memory, so a special hidden area is used for the call return stack. It only allows calls to be nested up to 5 deep, but that should be enough. That probably all sounds pretty dull, but what it means is that we can create new instructions to do exactly what we want to do. I'm using call and return here to make a more easily understood model of a dice. We call shake repeatedly. It's meant to be like someone shaking a dice in a cup. Then we call roll, which is when the dice gets rolled out onto the table. Now the rest of the program doesn't need to know whether we're counting from 0 to 5 repeatedly or counting and wrapping. Roll could even be prompting a human to roll a real dice and type in its value, just as long as it ends up in R1. This is an important concept, broadly called modularity, that a program is made up of modules. The program knows what each module does on the outside, but doesn't need to know about the details. Now let's add the display code. I used org40, origin 40, to force this code to start at slot 40. That way you can use the code you wrote after last video. If you wrote it. I can't help myself. I spotted a neat improvement on the version we started with. Adding hex FF has the same effect as subtracting 1. Remember, like an odometer. But this way, the carry flag will be set every time except when the value was 0. Each time we continue to loop, we know the carry is set, so we can rotate it straight into the lowest bit, lighting another LED. Now for the button handling. This is much as before, except we now keep the value displayed on the LEDs until the button has been released. I'm using a name for the button bit so that the code is a little easier to understand. I've also included a minimum display time, so even a short click gives you a chance to read the LEDs. Lastly, the initialization. Just one line of code to put the LEDs in output mode. The DDR register controls whether a pin is an input or an output. In output mode, the LEDs will be at full brightness. This is a little too bright for my liking on the Thinker Shield, but people using breadboards might have found the LEDs too dim. With the code written, we can assemble it to expand symbols and assign slot numbers. That's very compact, but not so easy to understand. You can use cut and paste to transfer to ArdEx, but it's better to use file transfer if your terminal supports it. Time to run it. Well, I think this can be improved. A real dice is quite easy to read, but with this line of LEDs, it takes a moment to tell a 5 from a 6. Obviously the LEDs are all in a line, but we can still use patterns that are easier to recognise. How about these patterns? 1, 2, 3, 4, 5, 6. Why not pause and work out their hex values? Getting these values with shifts and bit sets would be hard work, but I can think of two easy approaches. Here's a lookup table. That's all there is to it. We load the LED patterns into the lowest 6 bytes of RAM, and since R1 contains a value from 0 to 5, we just copy the contents of that memory cell to port B. Just 2 lines of code to store, but it uses 6 bytes of RAM, which is scarce in ArdEx. The other way would have been to do a jump table, where we jump to 6 different slots depending on the contents of R1. We'll use jump tables for some other problems. Let's run this code and see how it looks. Well, it's not brilliant, but it is easier to read. To be a useful dice simulator, you don't want to have to fire up your PC to run it. Let's add the finishing touches by having ArdEx automatically run the dice program whenever you plug in your Arduino. This save command saves program slots 0 to 41 to EEPROM on the chip. The RAM-S command saves the entire contents of RAM to EEPROM. The boot7 command tells ArdEx at startup to load the program slots and the RAM from EEPROM and start running at slot 0. Now you can press the reset button and the DICE program will be running, waiting for your button press. Same will happen if you power the Arduino from a dumb USB charger or a wall wart. And don't worry, you can always get back to the ArdEx prompt if it's powered up by a PC. You just need to hit Ctrl-C. If you want to disable the auto boot, run the command boot 0. That's enough for this video. 2 really big ideas to take away. Firstly, the really brilliant idea of call and return and programming in modules. Secondly, the almost as brilliant idea of the lookup table. Anytime you're having bother writing instructions to do a task, it's a good idea to see if a lookup table will help. No homework this time, but you might try changing the patterns by storing different values in the first 6 bytes of RAM. You'll soon see how flexible it is. Another thing that might be fun is to change roll to use out to print a question mark and in to accept a digit typed at the keyboard. You could then roll a real dice and type in its value. Might also be handy for testing different display patterns. Have fun.